Welcome, everyone. Today, we're diving deep into the SRE toolkit, exploring essential strategies to achieve that coveted 99.99% uptime. This isn't just about keeping the lights on. It's about engineering a resilient system that can withstand the unexpected. Our journey begins by truly defining what 99.99% uptime means in practice. It translates to just over 52 minutes of downtime per year. Think about that. The SRE mandate isn't merely to react to outages, but to proactively engineer reliability into every layer of our systems. This means shifting from a reactive firefighting mode to a strategic preventative approach. At its core, the SRE toolkit relies on two powerful pillars: robust automation and intelligent monitoring. These aren't just buzzwords. They're the foundational elements that empower us to scale, maintain consistency, and recover swiftly from issues. Our ultimate goal here is to move towards proactive system health. We want to identify and mitigate potential problems before they impact our users, ensuring a consistently smooth experience. Let's peel back the layers and see how we achieve this. Before we dive into any tools or code, we need a solid foundation. How do we measure reliability? This is where service-level objectives, or SLOs, come in. An SLO is a target for a service's reliability, like 99.9% of requests must complete within 200 milliseconds. It's a clear, quantifiable goal for how well your service should perform. To measure against an SLO, we need service-level indicators, or SLIs. These are the direct measures of a service's performance. For instance, if your SLO is about latency, your SLI might be the percentage of requests served under 200 milliseconds. SLIs provide the raw data that tells you if you're meeting your objectives. Now, here's where it gets interesting: error budgets. This concept acknowledges that no system is 100% reliable. An error budget is the maximum allowable downtime or performance degradation for a service over a period, derived directly from your SLO. If your SLO is 99.99% availability, your error budget is the 0.01% of allowed unavailability. This budget isn't just a number, it's a powerful governance tool. When you're within budget, you can take calculated risks, deploy new features, or experiment. But if you're burning through your budget too quickly, it signals that reliability work must take precedence over new feature development. This becomes the true foundation for proactive SRE. Now, let's look at how automation helps us achieve these reliability targets. A robust CI/CD pipeline is non-negotiable for SRE. Here, we see a simplified Python script that could be part of a larger CI/CD workflow, demonstrating a deployment step. The deploy to environment function encapsulates the logic for deploying our application. This script highlights critical elements like immutable infrastructure. Notice how we're building a new artifact and deploying it, rather than modifying an existing running instance. This ensures consistency and prevents configuration drift. Crucially, before any deployment, we have automated testing gates. The run tests function, even if simplified here, represents a suite of unit, integration, and end-to-end tests that must pass. No green light, no deployment. This catches issues early. And what if something goes wrong after deployment? We need clear rollback mechanisms. The rollback deployment function is a placeholder, but in a real system, it would automatically revert to the last known good state, minimizing downtime. This script is a blueprint for reliability baked into our release process. With automation handling deployments, let's shift to the other pillar: monitoring. How do we know our systems are healthy? This code snippet shows a simplified Prometheus.yml configuration, which is central to metric collection in many SRE toolkits. We're defining scrape targets, telling Prometheus where to find the metrics from our services. Each job name represents a different service or component we're monitoring. Beyond just collecting, we need to be alerted when things go wrong. While not explicitly in this snippet, this configuration works hand in hand with Alert Manager to define alerting rules. For example, an alert could trigger if a service's latency exceeds its SLO for a sustained period. These collected metrics are then used for dashboard visualization, typically with tools like Grafana. Imagine a dashboard showing real-time latency, error rates, and resource utilization for all your services. This provides immediate operational visibility. Ultimately, this setup allows for real-time anomaly detection. Instead of waiting for users to report an issue, we can identify deviations from normal behavior and respond before they escalate into critical incidents. This proactive stance is key to achieving that 99.99% uptime. So, we've explored automation for reliable deployments and robust monitoring for system visibility. How do these pieces fit together to deliver 99.99% uptime sustainably? It's all about interconnected strategies. Automation isn't just about deploying code. It's about automating incident response, scaling infrastructure, and even running synthetic tests. Monitoring isn't just about pretty graphs. It's about feeding data back into our automation to trigger auto-remediation or scale-ups. This creates a powerful continuous feedback loop. Our monitoring system detects an anomaly, triggers an alert, which might then initiate an automated remediation script or prompt human intervention. The outcome of that intervention, whether successful or not, feeds back into improving our automation and monitoring rules. This loop is also where incident response and postmortems become critical. Every incident, regardless of severity, is an opportunity to learn. Non-blaming postmortems analyze what went wrong, identify systemic weaknesses, and lead to actionable improvements in our automation, monitoring, and processes. By continuously refining this loop, we move beyond just fixing problems to preventing them, ultimately achieving sustainable reliability. This isn't a one-time setup. It's an ongoing commitment to engineering a resilient and highly available system for the long haul.